Let's consider separation of variables in more than two dimensions. So let's consider the cube with sides L, and the sides are held at temperature equal to 0 except the top, as shown here. And what we're interested in is what is the steady state temperature in the cube. So if you recall in the heat equation says that the rate of change of the temperature U is equal to the second derivative, or the Laplacian, of the temperature. If we're interested in steady state solutions, then U doesn't depend on time. And so the heat equation just becomes the Laplacian of U with respect to x, y, and z is equal to 0 inside of the cube. So we're really just solving Laplace's equation here instead of the more general heat equation, which had time dependence. So if you recall writing out Laplace's equation, so Laplace's equation is written as a bunch of partial derivatives. So the second derivative with respect to x plus the second derivative with respect to y plus the same with z, and that all adds up to 0. So we want to solve this equation. Before we go about doing that, let's list the boundary conditions of our problem. So in the x direction, we have that the temperature at the left side of the cube, x equal to 0, is 0. And also at x equal to L, U is equal to 0. In the y direction, at y equal to 0, we have 0 for the temperature, and same thing at y equal to L. And in the z direction, also at z equal to 0, at the bottom of the cube, we have 0 for the temperature. But at the top, at z equal to L, we have U naught, whatever this constant temperature is at the top. Okay, to solve a problem like this, we're going to, of course, separate variables like we would do in any type of solution to Laplace's equation. We just have one extra dimension. So now we'll write U as capital X, which is only a function of x, capital Y, a function of y, times capital Z, a function of z. Insert this into Laplace's equation, and then you get that the derivatives only act on one of these functions, either the x, the y, or the z. So you get x double prime times y times z plus x y double prime times z plus x y z double prime, where here a prime is derivative with respect to the coordinate of that function. So x double prime means a second derivative with respect to x. We can make this simpler by dividing by x, y, z. And so then you get this kind of familiar looking expression where you have x double prime of x divided by x, plus the same thing for y and same thing for z. And so this is a function of x plus a function of y plus a function of z. And the only way that this can be true is if each individual term is a constant. And so that means, for instance, x double prime over x, which is we said was a function of x, that actually has to be a constant. We'll write it as minus k squared. For y, you have a similar thing, except the constant here we'll write as minus p squared. For z, you in principle have the same thing, but z is not independent of the others, because all of them have to add up to 0, and so we can write the z equation as z double prime over z is equal to p squared plus k squared. Again, because it's not really independent of the x and y. We can't choose that constant independently. So why did we choose negative k squared or negative p squared here? Why not choosing plus k squared or plus p squared? So let's just take a minute to review why that would have been true and why choosing a positive constant here would have been a bad idea. So we chose the negative constant, so that would be x double prime of x is equal to minus k squared big X of x. And the solution here are sines and cosines. So this is, for instance, a cosine of kx plus b sine of kx. Let's imagine instead we chose that the constant was positive, so we chose plus k squared. In that case, the solution are not cosines and sines, but rather they're exponentials. A e to the kx plus b e to the minus kx. In this case, then, what we need to do is we need to think about our boundary conditions. So we need to choose the constant that will allow us to solve the boundary conditions. So if you recall, our boundary conditions were that at x equal to 0 and x equal to L, our function u must be equal to 0. But that says that big X must be 0 at 0 and L. And if you think about that, that's impossible to solve with the sum of exponentials. The sum of the exponentials has to be positive. Well, it could be 0 at one point, but it's not going to be 0 at 2 points. In contrast, sines and cosines have multiple zeros, and so you can actually make that happen. So that's why we have to choose a negative constant, minus k squared, for the second derivative of x. So again, our solutions then are a cosine of kx plus b sine of kx. Let's go through imposing our boundary conditions like we usually do with separation of variables. And so, for instance, impose the first boundary condition at x equal to 0, namely x at x equal to 0 must be 0. That tells us then that we have a cosine of 0, since sine of 0 is 0, which is just a must be 0. So that means a itself is 0, and our solution for x now simplifies to just b sine of kx. We can do the same thing for x equal to L, and now at L we have b sine of k times L, and we need that to be 0. The only way that could happen is if k times L was some multiple of pi. Or you could write that as k is equal to n pi over L. So putting that together then, we have for capital X, our function x is b sine of n pi x over L. We don't know what this constant b is at this point. Okay, so we can do a similar thing for the y direction. So let's look at the y double prime as a function of y over y, and that's equal to minus p squared. So p here is different than k. So again, a similar reasoning leads us to a similar solution. I'm not going to go through all the steps. I'm just going to state that final solution where y is now b, which is a different constant, sine of m pi y over L. Notice I used m, not n. So m here is different than the n that we had in the x direction. In particular, the x and y directions are independent of each other. You can choose a different constant here, and you can always solve the boundary conditions. They might be the same, like n might be 1, m might be 1, but they don't have to be. So they, in principle, are different integers. So the x and y directions are independent. That's a really important consequence in a bit. So to summarize, we have as our solution for x, y, and z, for the temperature, we have, it's written as capital X times capital Y times capital Z, where we found capital X to be b sine of n pi x over L. Capital Y was some other constant b, let's call it b twiddle, sine of m pi y over L. And the z equation is z double prime over z is now equal to k squared plus p squared, where k is, as we found, n pi over L, and p is similarly something like m pi over L, just following the same reasoning. So clearly we need to solve our equation for z of v. So let's rewrite that equation. We have z double prime as a function of little z is equal to n pi over L squared plus m pi over L squared times capital Z of z. This is going to be annoying to keep writing, so let's rename this. Let's call this lambda mn squared. So rewriting our equation, we have z double prime is equal to lambda mn squared times z. So it depends on m and n, but now it's a little simpler to write. Clearly the solution here are indeed exponentials, and so we have c e to the lambda mn times z plus d e to the minus lambda mn times z. Okay, so let's impose our boundary conditions now. So our boundary conditions in the z direction, looking back at what we had that u at x, y, and z equal to 0 must be 0. That means that capital function z must be 0 at z equal to 0. So putting z equal to 0 in our solution, we have c plus d must be equal to 0, or c is equal to minus d. So we can then write this in terms of one arbitrary constant, c, e to the lambda mn z minus e to the minus lambda mn times z. There's a really nice combination that is useful here. So the function sinh is 1/2 e to the x minus e to the minus x. So we can use that to rewrite this z function in terms of the sinh. So this is 2 times c sinh of lambda mn times z. Or you can absorb that factor of 2 into the unknown constant and just call that c twiddle. Sinh of lambda mn times z. In principle, we have one more boundary condition that we need to impose in the z direction. So at z equal to L, we need this to be equal to a constant, u naught. We can't actually solve this boundary condition at this point, so we need to wait on this one. We're going to need to use our ideas of a Fourier series in order to find the solution to this. Okay, so let's summarize again where we are after all of this work. So we've written our function for the temperature u of x, y, and z inside the cube as x times y times z, which are functions. And we found those functions, and so we can write this as b sine of n pi x over L, b twiddle sine of m pi y over L, and c twiddle sinh of lambda mn times z. It's useful, we can just collect all of these unknown constants into, let's call it some kind of superconstant, where the superconstant d is just equal to b times b twiddle times c twiddle. Okay, so we really only have one unknown constant in all of this. So u is just d times our sine functions and times our sinh function. Recall that this lambda mn, it's useful to just write it down here so we can remember what it is given by these n pi over L squared, m pi over L squared, and it's actually the square root of all of that. So we define lambda squared to be the sum of those squares. So, of course, remember that the sum of a set of solutions is still a solution to Laplace's equation. And so we can actually write this as a sum of solutions. But since we have two integers, n and m, we can sum over each of them independently. So we have a double sum over n and m. Our constant now is a constant with mn dependence, and then we have our sine functions and our sinh functions. In our next video, we're going to look at how we end up solving for the unknown coefficients and how we go further to imposing our boundary condition.